This is the lecture for the first part of section 4.5, Irreducibility in Q bracket X. In this section, we want to develop results for determining when a polynomial with rational coefficients is irreducible in Q bracket X. We first note that by multiplying through by the least common denominator of its coefficients, a polynomial with rational coefficients can be transformed to a polynomial with integer coefficients. For instance, suppose f of x is the polynomial 3/5 x cubed minus 2/3 x squared plus 1/4 x plus 1/10. The least common denominator of the coefficients in f of x is 60, and multiplying f of x by 60, we obtain 36x cubed minus 40x squared plus 15x plus 6. So that's a polynomial with integer coefficients. We can state this as a general result. For all f of x in Q bracket x, there is an integer c not equal to 0 such that c f of x has integer coefficients. Since c f of x has the same roots as f of x for any constant c not equal to 0, then finding the factors of f of x is equivalent to finding the factors of c f of x. This means that factoring in Q bracket x can be reduced to factoring in z bracket x. Our first theorem gives us a test for determining the possible rational roots of a polynomial with integer coefficients. This is theorem 4.21, the rational root test. Let f of x be the polynomial a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus down to a1x plus a0 be a polynomial with integer coefficients. Let r over s be a rational number not equal to 0 in lowest terms. If r over s is a root of f of x, then r divides a sub 0, which is the constant coefficient, and s divides a sub n, which is the leading coefficient. To prove this, we'll start off supposing r over s is a root of f of x. We then need to show our conclusion r divides a0 and s divides a sub n. Since r over s is a root of f of x, then f of r over s, which is the expression shown, is equal to 0. Multiply both sides of this equation by s to the n to clear the denominators, and we obtain a sub n r to the n plus a sub n minus 1 r to the n minus 1 s plus down to a1 r s to the n minus 1 plus a0 s to the n equal to 0. We'll label this equation star. And solving for the last term on the left and then factoring r, we obtain a sub 0 s to the n is equal to the given expression, and factoring an r out, we'll have the next line. Now, since r is a factor on the right side, then it also divides the left side, so r divides a sub 0 s to the n. Now we're supposing that r over s is in lowest terms, which means that r and s have no factors in common. So in particular, r and s have no prime factors in common. It then follows that r and s to the n also have no prime factors in common. A common prime factor of r and s to the n would also have to be a common prime factor of r and s. And this implies that the GCD of r and s to the n is 1. Now, since r divides a0 s to the n and the GCD of r and s to the n is 1, then it follows from theorem 1.4, way back in chapter 1, that r divides a0. And this is the first part of our conclusion. To show the second part of our conclusion, s divides a sub n, we'll start over again with equation star. This time we'll solve for the first term and then factor s to obtain a sub n r to the n is equal to the given expressions. And this shows that s divides a sub n r to the n. S divides the right side, so it must divide the left side. And once again, since r over s is in lowest terms, we can conclude that the GCD of r to the n in s is 1. And since s divides a sub n r to the n, and the GCD of r to the n in s is 1, it then follows from theorem 1.4 that s divides a sub n. And this is the second part of the conclusion, and this completes the proof of the theorem. For an example, we can use the theorem to factor the polynomial f of x is 2x to the fourth plus 5x cubed minus 8x squared minus 8x plus 3 in cube bracket x. Now, by the factor theorem, each root will correspond to a linear factor. To determine the roots, we can apply the rational root test. Suppose r over s is a rational root of f of x. By the rational root test, the numerator r must divide the constant coefficient 3, and the denominator s must divide the leading coefficient 2. So r divides 3 and s divides 2. So r is either plus or minus 1 or plus or minus 3, and s is plus or minus 1 or plus or minus 2. And then the possible rational roots are r over s will be plus or minus 1/2, plus or minus 1, plus or minus 3/2, plus or minus 3. So we can take either plus or minus 1, plus or minus 3, the values for r, over plus or minus 1 or plus or minus 2, the values for s. So we have 8 possible rational roots. And we can test these one by substituting into the formula for f of x to see if any are in fact roots. To test if minus 1/2 is a root, we can compute f of minus 1/2, which will be 2 times minus 1/2 to the fourth, plus 5 times minus 1/2 cubed, minus 8 times minus 1/2 squared, minus 8 times minus 1/2 plus 3. And this is 1/8 minus 5/8 minus 2 plus 4 plus 3, which works out to 9/2. Now, since f of minus 1/2 is not equal to 0, then minus 1/2 is not a root of f of x. So we have 8 possible rational roots, and we can go through this procedure for each of the 8 roots. Now, it's quite a bit of work sometimes to evaluate the polynomial at each root by substitution. So alternatively, we can use synthetic division to divide f of x by the corresponding linear factor, and this is sometimes quicker. So to divide f of x by x plus 1/2 using synthetic division, we'll start by writing minus 1/2 along with the coefficients of f of x arranged as shown. So we've got minus 1/2 in the upper left corner, and then the 5 coefficients of f of x written as indicated. We start by pulling down the first coefficient to the bottom row, so we'll pull the 2 down. Multiply the divisor, minus 1/2, times the first entry in the bottom row, and we'll put the result below the second coefficient. So minus 1/2 times 2 is minus 1. And then we add the entries in the second column. Now, very important, don't subtract these entries. We're going to add, so we obtain a 4. Then we'll multiply minus 1/2 times the second entry in the bottom row and put the result below the third coefficient. So minus 1/2 times 4 is minus 2. And now we'll repeat this procedure. So we're going to add the entries in the third column. Minus 10, multiply by minus 1/2. Add the entries in the fourth column. Minus 3, multiply minus 3 by minus 1/2. And then add the entries in the fifth column. Now this tells us that when f of x is divided by x plus 1/2, the quotient is q of x is 2x cubed plus 4x squared minus 10x minus 3. We can read those coefficients off of the bottom row. And the last entry in the bottom row is the remainder. So the remainder r of x is 9/2. And since the remainder is not 0, then x plus 1/2 does not divide f of x, and hence minus 1/2 is not a root. Now, testing the other possible rational roots, we eventually find that minus 1 is a root, and we can check that by synthetic division. And we see that we obtain a remainder of 0. This tells us that minus 1 is a root, and f of x is x plus 1 times 2x cubed plus 3x squared minus 11x plus 3. And once we find one root, we can test the remaining possible rational roots on the quotient polynomial. And we'll eventually find that 3/2 is a root. And checking this using synthetic division, pull down the 2, multiply by 3/2, add, we get a 6. Multiply by 3/2, we'll get a 9. Add, minus 2. Multiply by 3/2, minus 3. And we obtain a remainder of 0. And then f of x is x plus 1, x minus 3/2 times 2x squared plus 6x minus 2. Factoring a 2 out of that third factor, we obtain x plus 1, x minus 3/2 times 2 times x squared plus 3x minus 1. It's straightforward now to check using either synthetic division again or the quadratic formula that the quadratic factor x squared plus 3x minus 1 has no rational roots, so is irreducible in Q bracket x. So we've factored f of x completely in Q bracket x. For another example, we can use the rational root test to show that g of x equal x cubed plus 5x plus 1 is irreducible in Q bracket x. And according to the test, if r over s is a rational root of g of x, then r must divide the constant coefficient 1, and s must divide the leading coefficient 1. So the only possible rational roots are going to be r over s is plus or minus 1. And we can check both of these by substitution. G of minus 1 is minus 1 cubed plus 5 times minus 1 plus 1, which is minus 5. And g of 1 is 1 cubed plus 5 times 1 plus 1, which is 7. And neither is a root. And therefore g of x has no rational roots. And since g of x has degree 3, it follows from corollary 4.19 that g of x is irreducible in Q bracket x. Now, we can use the rational root test to give a proof that square root of 2 is irrational. Let's let f of x be the polynomial x squared minus 2. Then obviously f of x is in Q bracket x. And if r over s is a rational root of f of x, then r must divide the constant coefficient, which is 2, and s must divide the leading coefficient 1, so that r is plus or minus 1 or plus or minus 2, and s is plus or minus 1. And therefore, the possible rational roots of f of x are r over s plus or minus 1 or plus or minus 2. Now, since f of plus or minus 1 is just plus or minus 1 squared minus 2, which is minus 1, and f of plus or minus 2 is plus or minus 2 squared minus 2, which is 2, then none of these are roots, which implies that f of x has no rational roots. However, square root of 2 is clearly a root of f of x, which tells us that square root of 2 must then be irrational.